Today we are presenting our ICCV paper, Temporal-Aware Latent Brownian Bridge Diffusion for Video Frame Interpolation. So the definition of the frame interpolation task is that we're given two consecutive video frames and we want to predict the intermediate frame, which is IN. Usually we set N equals to 0.5 to predict the very middle frame. Next, let's go through the background knowledge of the diffusion model. The diffusion model contains two processes. One process is the diffusion process, which gradually adds noise to the image until it achieves a random noise. How it adds noises is based on the given normal distribution, and the time step t takes value in 1, 2, 3 until 1,000. And the constant alpha bar t is predefined. It ranges from 1 to 0 and in decreasing order. So when t is very large, alpha bar t is just very close to 0, and we can see that in this formulation it will be a normal distribution with zero mean and identity covariance matrix. Another process in the diffusion model is the sampling process, which gradually denoise a random noise to back to the image. How it achieves the denoising is by reverse the diffusion process. So given a xt, we want to compute xt minus 1 given a formula. And this can be extended to all the time steps where we have the formula which is defined here. And in this formula, xt is a known term. And the values of alpha t, alpha bar t, and the sigma t, all of them are predefined constants. So the z here is a random Gaussian noise, which is sampled from the standard Gaussian distribution. So the only unknown term here is the epsilon theta t. Epsilon theta t is the neural network that predicts epsilon, where epsilon is the value that we used to obtain xt from x0. So with this formula, we can compute xt minus 1 given given xt, and extending that to all the time steps, we can finally denoise a random noise to a image. Another important background information is the latent diffusion model. So here we have a encoder that encodes the image into the latent space, and the height and width is therefore reduced. And the diffusion process and the denoising process is run in the latent space with a better efficiency. And we also have a decoder that decodes the latent back to that image after we run the sampling process. So our motivation of our method is that video frame interpolation has been formulated as a generation task. But the problem is image-based diffusion methods lack of explicit extraction of temporal information, so they only deal with spatial features. But video diffusion models usually require extremely high computational costs. Our goal is to enable the temporal feature extraction while keep the computational cost reasonable. Our method for the diffusion model is the Brownian bridge diffusion. The Brownian bridge diffusion contains diffusion process and sampling process defined in the given formula. How it is achieved is by defining x0 to be the video clip, the encoded video clip, and x capital T to be the encoded video clip with a zeroed out middle frame, as shown in the image. And the diffusion process is a very standard definition, and we have the sampling process that is defined here, So the only unknown term here is actually xt minus x0. And similar to the standard diffusion model, we estimate this with a 3D unit. So the 3D unit is a unit that consists of 3D convolution and tension, where we can extract temporal information. Delta t here is defined as the capital T over the number of sampling steps. Here we set, in our experiments, we set capital T equals to 2 and the number of sampling steps equals to 10. Then we also design a autoencoder that enables the temporal feature extraction. So first we have a shared image encoder that reduces the height and width of the given video clip. And the encoder features at each layer of the image encoder are sent to the image decoder to assist the decoding process. And we extract the temporal information in the latent space with some 3D convolution and attention. However, in this architecture, we can only extract the temporal information in the latent space. So we include a 3D wavelet transform to extract the temporal information in the pixel space. And we also take advantage of the optical flows to guide the autoencoder to predict the middle frame. The autoencoder is trained with the loss with L1 loss and LPIPS loss with VGG features. During inference, we replace the middle frame by zeros and we pass it to the image encoder and then to the Brownian bridge diffusion. So the Brownian bridge diffusion, as we previously defined, it connects the 4 video clips and the video clips with the middle frame zeroed out. So after the Brownian bridge diffusion, we are predicting the original video frames, and finally we decode the image back, the latent back to the image. Here is our architecture details. At each level of the decoder, so here we have the encoder feature and a warp version of the encoder feature. The warp version means that we warp the encoder feature based on optical flows, and we concatenate them to in the channel dimension and merge them with the decoder feature via cross attention. And in the temporal blocks, we have a 3D convolution and a 3D self-attention. In the encoder temporal block, we only have self-attention, but in the decoder temporal block, we have a temporal cross-attention that aggregates 3 frames into just one single frame. And in our design of the 3D wavelet feature, in the 3D wavelet transform, we first extract the temporal information with 3D wavelet transform, and we pass it to a wavelet encoder, which consists of several convolutions to map it to the same size of our latent features. And they are multiplied. They are passed to a sigmoid activation functions and multiplied with our latents in a element-wise sense, and then it is added back to the latent feature. Here we have our quantitative evaluation results. Note that PR-VFI is trained with actual data, so we excluded it from the ranking. And we also achieved the best efficiency among the diffusion models. For example, we achieved a very small number of parameters. We only have 46.7 million of parameters, and we only train with 55,000 of triplets. And here we have our qualitative results, and we can see that our interpolation results is in all the cases it is better than other sodas. We have some extra qualitative results here. Here we have a qualitative results showing in a video form. Here we have some qualitative examples. And thank you for watching.